Okay, so now on to example 2, where we're only going to find the solutions in a certain interval. So most commonly, we're asked to find solutions in 0 to 2 pi for our interval, although we could choose a different interval. So example A of the second example, sine alpha times tangent alpha equals sine alpha. So I want to talk about a common mistake that a lot of students make in a problem like this, and that is to just divide both sides by sine alpha and then conclude that tangent of alpha has to equal 1. Well, it's true that tangent of alpha does need to equal 1 for this to possibly be true, but there's another situation here, and that gets lost if you divide by sine of alpha. So you want, instead of dividing by sine of alpha, you want to move sine alpha to the other side and set this equal to 0. And this is a factoring problem, so we want to factor. And if you factor out sine alpha instead of dividing it, notice there's another situation here. Tangent of alpha equals 1 isn't the only thing that will yield solutions. Also, when sine of alpha equals 0, we'll get solutions. So this implies that either the sine of alpha equals 0 or tangent of alpha equals 1 gives us solutions. So sine of alpha equals 0. Now, we only want the solutions in 0 to 2 pi, right? So where in one trip around the unit circle is the sine equal to 0? Well, that would imply that alpha is either 0 or pi. And that's it. We don't have to add the period. We just want those two main solutions. Then tangent of alpha equals 1 would be true when alpha is pi over 4 in quadrant 1 or 5 pi over 4 in quadrant 2. So the we only have 4 solutions here. All right, so it's really important that you don't do what I talked about in the beginning, divide by sine alpha, because if you had done that, you would only get these 2 solutions. But notice this is true, you know, sine of 0 is 0, so this 0 equals 0 is true. Same with the pi, you get a true statement. For pi over 4, no, of course, these are the same on both sides, right? So when tangent of alpha is 1, that'll make this equal to this true. And likewise with 5 pi over 4. So there's really 4 solutions. You want to make sure you get all 4 of those. And if you divide by the function, that doesn't happen. So in general, you never want to divide by the function itself, or one of the 6 functions, of course. You want to move everything to one side and factor instead. All right, let's move on to B. So we've got sine squared u equals 2 minus the sine of u. So notice these problems in this next group, I've got a little more complicated things happening. We can't just simply isolate sine of u here. But notice we have a sine of u is squared and then sine of u to the first and a constant. So this is like a quadratic pattern going on here, or what we call quadratic form. And when that happens, you want to move everything to one side. So sine squared u plus sine u, and then subtract 2, set it equal to 0. And again, we want to factor then. Right? So note we've got the sine squared, and then the sine to the first power, and then the constant. That's a quadratic form. So when we factor, we're factoring like this is a trinomial. Of course, it's not a polynomial, right? It's in sine, not in x or y or anything like that. But we treat it like it's a polynomial. Sine of u times itself will give us sine squared u. So sine u goes in the first two spots. And then we looked for factors of -2 that add up to 1. That would be +2 and -1. So if you distribute all this, or FOIL if you will, you're going to get this 3-term expression in sine u. Sine u times sine u is sine squared u. And then our outside product would be negative sine u. Our inside product is +2 sine u. That adds up to sine u. 2 times -1 is -2. Alright, so the reason we factored is now we can set each factor to 0, right? And this has to be a 0 here for this to work. If this isn't a 0, we can't make the following conclusion. That the first factor is equal to 0 or the second factor is equal to 0. Right? Because this times this equals 0 means one of these things has to be 0. All right. Well, the first equation gives us then that now we can isolate the sign, right? And the first one tells us that this is true if the sine of u is equal to -2, and the second one if the sine of u equals 1. So look at those and think about those for a second. And hopefully you come up with, or you realize in the first equation, this doesn't make any sense. This has no solution because sine u, or sine of anything, is between -1 and 1. -2 is outside of the range of the sine function. But that doesn't mean this equation doesn't have any solutions. It just means this factor doesn't yield any. But this one does. Sine of u equals 1, that has solutions. In fact, exactly one solution in 0 to 2 pi, u would equal 3 pi over 2. And that's our only solution, right? Sine is only 1 once in 0 to 2 pi. So only one solution to that one. All right, let's go on to C. No, D, I'm sorry, that was... No. That was B. We are on to C. Okay. C. 2 sine squared t minus cosine t minus 1 equals 0. Okay. So this one is trickier than the last one because we have two different functions. It sort of looks quadratic, right? You got the squared and then the first and then the constant, but they're different functions, so it doesn't work to use factoring like this. So when something like this happens, we have to look to our identities. And think of an identity that relates sine and cosine, and we don't want to bring in any other functions, so just think of just the identities that involve those. Of course, we have they're co-functions of each other, but we don't want to bring in a different angle, right? You'd have to replace with a pi over 2 minus t, and that would just complicate things. So don't look to those. The natural choice is to use our Pythagorean identity that relates sine and cosine. And of course, sine squared t plus cosine squared t equals 1. And no, don't take the square root of both sides here. That would be totally wrong. So that doesn't mean sine t plus cosine t equals 1, right? So it would be really complicated to replace cosine t in terms of sine because you'd have to take a square root. You'd have a square root in here, and that would be messy. So what we'll do instead is replace sine squared t with an expression in cosine squared t. Sine squared t is 1 minus cosine squared t. Okay. So 2 times 1 minus cosine squared t minus cosine of t minus 1 equals 0. Distribute the sign through 2 minus 2 cosine squared t minus cosine t minus 1 equals 0. And then we've got everything in terms of cosine. It's quadratic in cosine t, so we're going to have to do it like the last problem now. But now it's manageable because these are the same functions, right? We need to simplify before we're ready to factor. 2 minus 1 is plus 1. And then if I'm going to factor, I prefer to factor when this is a positive. So I'm going to multiply both sides by -1 now. Can always just change the signs of all the terms, right? And that'll make my factoring easier. And of course I still get 0 on the right. Alright, now I'm ready to factor. So 2 cosine squared t, that would have to be 2 cosine t times cosine t. And now I need factors of -1 here. Of course, it's got to be a +1 and a -1. I just got to get the plus and the minus in the right spot. Since I want to get a plus here, this one will have to be plus and this one will have to be minus. Whoops, I already wrote the 1. Let's put a minus in there. So that I get 2 cosine t minus cosine t adds up to cosine t. Alright, so now I have my two factors set equal to 0. I can just set both factors to 0. So this one, to solve for cosine t is 1/2. And this one's already isolated. So I'm ready to find solutions. Again, only looking in 0 to 2 pi. Cosine of t is 1/2 when in quadrants 1 and 4, excuse me, and that would be when t is pi over 3 or 5 pi over 3 in quadrant 4. Now, if I were looking for all solutions, I would just say pi over 3 plus 2 pi k, 5 pi over 3 plus 2 pi k, right? But I don't need to do that if I only want solutions in 0 to 2 pi. Cosine of t equals -1 when t is pi. So there are my 3 solutions, right? This only has one solution in 0 to 2 pi. All right, in D, so again we have a problem with having two different functions, cosine theta minus sine theta equals 1. And I talked about in this previous problem how it would be difficult to just replace cosine t in terms of sine t because you would have to take the square root of both sides, and that gets messy. We don't really want to bring a radical in. And so this one, excuse me, would, whether we replace sine with cosine or cosine with sine, that's what we would have to do using the Pythagorean identity. We'd have to take the square root and we'd have a radical. So there's a little technique that we can use to avoid that, and what we can do here is square both sides of this equation. Now actually, if you bring the radical in, that's what you would have to do anyway. So instead of bringing the radical in, we'll just square both sides now. So square both sides. Now you may remember this from algebra, that whenever you square both sides of an equation, things get a little tricky because you can bring in new solutions that don't actually work in the original equation. So for example, like if x squared equals 4, x equals 4, and then you square both sides, x squared equals 16. This, of course, only has a solution 4. This has a solution 4 and -4. Well, -4 doesn't work in the original, right? So we have to watch for these extraneous solutions now. That's what we call solutions that don't work in the original equation. So they'll need to be thrown out. All right, so when we square both sides here, remember you have to distribute. So a common mistake people make is just say cosine squared plus sine squared theta, but that's not what we get. So write it down twice if you have to, right? This squared equals this times itself, and then distribute. Cosine times cosine would be cosine squared theta, and then our outside 2 will give us minus cosine theta sine theta. Inside 2, same thing, minus cosine theta sine theta. And then our last two negatives become a positive, and we get sine squared theta equals 1. Excuse me. Notice these two middle ones are like terms, so we're going to add those up. Oops, two of those, right? Okay, well that looks more complicated than what we started with. But notice you have cosine squared theta plus sine squared theta here. And those two expressions always add up to 1. So we're going to replace that with 1. Whoops. Started subtracting 1 already. That equals 1. So then when you subtract 1 from both sides, those will cancel. And we just get negative 2 cosine theta sine theta equals 0. Which is the same as 2 cosine theta sine theta equals 0. That negative doesn't really affect anything. And neither does the 2 for that matter. You could just divide the 2 off. So this is going to be true, right? Think about this equation here. You got three numbers, 2 times cosine theta times sine theta. They're all multiplied together. This is only going to be true if either cosine theta equals 0 or sine theta equals 0. Right? The 2 isn't going to create a 0 there. You can divide it off if you want. All right, so now again, just on 0 to 2 pi, where is the cosine theta equal to 0? That would be when theta is pi over 2 or 3 pi over 2. And then sine theta equals 0 when theta equals pi. Excuse me. Well, just because I like things in order, I should put 0 first and then pi, right? And you might be thinking, what about 2 pi? But notice in the problem, I did not include 2 pi because it's coterminal to 0. So we won't include 2 pi, okay? Because that's already, we only want to think about that happening one time in one trip around, not 2 times. And 2 pi is coterminal to 0. Okay, so we have those 4 solutions. And you'd be tempted to just circle those. But here's where we need to check for the extraneous solutions because we did square both sides. So let's check these. And when you check, you want to go back to the original equation, which was cosine theta minus sine theta equals 1. So let's check theta equals pi over 2 first. So cosine of pi over 2 minus sine pi over 2. This is 0 and this is 1. So notice what happens is we get negative 1, and that's not 1. So that solution needs to get tossed out. And of course, when you square negative 1, you get 1. That's why it showed up in the solution set. But we have to go back to before we squared. We need to check that, right? So that one gets thrown out. That one doesn't work. Theta equals 3 pi over 2. We've got cosine 3 pi over 2 minus sine 3 pi over 2, which is 0 minus sine of 3 pi over 2 is negative 1, and that does equal positive 1. So that one works. I'm just going to list the solutions here. So 3 pi over 2 works. Let's check 0. Cosine of 0 minus sine of 0. Whoops, I wrote theta instead of 0. I'm used to writing theta. Cosine of 0 is 1. Sine of 0 is 0. That equals 1. That one works. So 0 works. And you can probably see what's going to happen with pi. If theta equals pi, cosine of pi is negative 1. Sine of pi is 0. So negative 1 minus 0 is negative 1. That does not equal 1. So that one is also out. So just the 2 solutions work. I should put the 0 first. Bugs me when the numbers are in order, but that's okay. I'll leave it. So these two, just those two solutions are the only ones that work. All right, I'm going to take a little break here and we'll finish the last 4 problems or so.